Hi, this is the third lesson in nuclear decay. Go through the description of this video. All the useful and necessary links are given in my description of this video related to all other videos in my channel. Also, you can better go through the playlist of this channel. I classified all my 100 videos into 6 different units. Like Unit 1 past paper discussion, Unit 1 lessons, Unit 2 past paper discussions, Unit 2 lessons, and so on like that. So the name of those classifications each are given with home page of Unit 1 past paper discussion, home page of Unit 1 lessons, home page of Unit 2 lessons, home page of Unit 2 past paper discussions, and so on like that I classified. So it will be useful for you to choose the required video. Before watching this video, it's better to go through my first two lessons in nuclear decay. In my first lesson, I discussed about stability of the nucleus and binding energy. In second lesson, I discussed radioactive decay. Okay, so in my first lesson, I said the nuclear decay could happen in two different ways. Uh, the one, the first one I can say it as a natural decay that happens spontaneously. Example, radioactive decay. The second way the nuclear decay happens is artificial transmutation, in which human intervention is required, such as a nucleus must be bombarded by particles such as alpha particle or neutron or proton. So that will create the transmutation or change in the nucleus. So in third lesson, I'm going to discuss about artificial transmutation, and you know the well-known artificial transmutations are fission and fusion, nuclear fission and nuclear fusion. Okay, so in my this lesson, I'm going to discuss about artificial transmutation. For example, fission and fusion also will be discussed. So I'll start with a special type of artificial transmutation, nothing related to fission or fusion. This question appeared in January 2015. Unit 5 paper, WPH05 paper, Edexcel, question 15, right? So before doing that question related to artificial transmutation, in that question, aluminium nucleus is bombarded by an alpha particle, which creates a phosphorus isotope and a neutron. So anyway, I'm going to calculate the energy release in that as the first first topic in this lesson. Then I'll go to nuclear fission, then finally nuclear fusion, right? Okay, so normally students, they ask when we calculate energy release, whether it's a radioactive decay such as alpha decay or fission, fusion, do we need to consider the total mass energy conservation, or do we need to consider the mass deficit? Normally students, they ask, because sometimes we need to use mass deficit. Most of the situations in the past paper questions, when you go through it, we use mass deficit, but sometimes we need to consider the total mass energy conservation also. So actually, you know, there's nothing called mass deficit or principle of mass deficit in physics. Okay, it's an observation made mainly in nuclear physics or particle interactions or nuclear interactions. So remember that there is nothing called a principle or like a conservation law, something like that. Mass deficit is not a law. It's actually an observation made in nuclear interactions. For example, when we consider alpha decay, better to start with that one, what I discussed in the previous lesson, in second lesson. Alpha decay, say for example XAZ, that's a parent nucleus, decays into a daughter nucleus A minus 4, Z minus 2 plus alpha 42, right? And energy is released. Sometimes books they say energy release, they denote by E. Okay, so here is it necessary to use always the mass deficit approach, or should I follow that mass deficit approach? Can't I use the total mass energy conservation? You know, I told in my first lesson that during all type of nuclear decay, 6 factors are conserved. We learned already those factors in unit 4 particle physics. One of it is total mass energy, momentum, then charge, baryon number, lepton number, strangeness. So these all are conserved in all type of nuclear decay, whether it's a radiative decay or artificial transmutation such as fission fusion. Anywhere, everywhere, total mass energy is conserved. So here, actually, total mass energy is conserved. There's nothing called mass deficit, principle of mass deficit or law of mass deficit. There's nothing like that in physics. But actually, what we are using the principle of conservation of total mass energy. And when we rearrange, we get a pattern that gives mass deficit. So that's the reason we normally all the mark schemes and books, they start with mass deficit, but it's not a principle. I'll show it first by using the law of conservation of total mass energy. That's actually mass has equivalent energy, energy has equivalent mass according to special theory of relativity. We learned that in unit 4 also. Okay, so here I can say in this reaction, alpha decay, total mass energy is conserved. That means initial total mass energy of X must be equal to total mass energy of Y plus total mass energy of alpha particle. That's all. That's a basic principle. Okay? So we can't add mass and energy because they are different units, is it? How can we add them? For example, if I want to add the mass of X with energy of X, I can't add it. So what should I do? I should convert the mass of X into equivalent energy of X. Then I can add it, is it? Because mass, the SI unit is kilogram, energy, that is joule. Kilogram and joule, we can't add it. But what can I do? I can convert the mass, its equivalent energy, could be added with kinetic energy of the particle X. Right, we'll see that way, whether it comes finally like a mass deficit. Okay, so total mass energy is conserved. Mass of X, C square. So that means I'm converting the mass of X into equivalent energy. Mass of X C squared plus kinetic energy of X. There's nothing else. So must be equal to this, the total mass energy of X. Must be equal to total mass energy of alpha particle at the daughter nucleus. Okay. So that I can say mass of Y C squared plus kinetic energy of Y plus mass of alpha C squared plus kinetic energy of alpha. Okay, so here what do we put like capital E? We normally say that is the energy release during radioactive decay. What type of energy release? Only the kinetic energy of both alpha particle and the daughter nucleus. So these two together I can write these two. This is kinetic energy of Y and kinetic energy of alpha. Both could be written as E, both together. So I'll rewrite that again. So that could be written as again like mass of X C squared plus kinetic energy of X equal to mass of Y C squared plus mass of alpha C squared plus E. E is the kinetic energy of the daughter nucleus, and kinetic energy of alpha I put it as E, that is the energy released during alpha decay, right? Okay, also we must know the parent nucleus, it's at rest. It won't be in motion before emission of alpha particle. Before the decay, the parent nucleus is at rest. So kinetic energy of X will be equal to 0. Now rearrange it. Mass of X C squared. Bring this to the left, minus mass of Y C squared minus mass of alpha C squared equal to E. So the minus sign, if I take it common, and c square also if I take it common, it will become max mx minus my plus m alpha c square equal to E. Now see here, what is this one? Mass of x minus mass of y plus mass of alpha. Mass of y plus mass of alpha is the total mass of the product. So initial mass, that's a mass of the parent nucleus, minus total mass of the product. This is called mass deficit. That's the thing we normally say, mass deficit. This we call mass deficit into c squared equal to E. So that's the way we normally do and find the energy release during alpha decay. So we normally start with this one. Mass of X minus total mass of the product, that is mass deficit into C square, we call it as energy release. Yeah, there's nothing wrong. But what I want to say here is there's nothing called a principle of mass deficit. Actually what we are doing here, we are using the law of conservation of mass energy. But when we rearrange, it comes like mass deficit. There's nothing wrong, but normally students they ask, do we need to use mass energy relationship or mass deficit method? Anything you can use, but both are the same. Actually, the basic principle is total mass energy conservation is the basic principle we are using. That's the law actually. But when we rearrange, it comes like mass deficit. You can start with this also. So whenever they ask to find the energy release during alpha decay, yes, you can start with this one. There's nothing wrong. Okay, but actually remember that there's nothing called principle of mass deficit or law of mass deficit. The only law which is related to energy is the total mass energy conservation. We are using that. Finally, we are ending up with the same format what you do normally in the class. Okay, so if you understand this basic principle, it will be useful when we calculate the energy released during any type of artificial transmutation or fission or fusion. It will be useful. So again, there's nothing called mass deficit principle, and we are just using conservation of total mass energy. That's the only principle we can use to find the energy release. But the pattern, when we rearrange, it comes like mass deficit. Okay, so remember that one. Okay, so this is the question this question appeared in January 2015, WPH05 question 15, number 15. So there artificial transmutation reaction equation is given. An aluminium nucleus is bombarded by an alpha particle, and the alpha particle has a kinetic energy of 5.3 mega electron volt. So the alpha particle has kinetic energy, and that also given. And the products are phosphorus isotope with mass number 30 and a neutron. The question is calculate the total kinetic energy released, total kinetic energy of the reaction product. So the total kinetic energy of the product. So that means there are any other form of energy like electromagnetic radiation or heat is not released. So that's a purpose. So they asked to find the total kinetic energy of the products. Okay, so the mass of the proton, neutron, alpha particle, aluminium nucleus and phosphorus 30 isotope are given in terms of unified atomic mass unit. Okay, how to approach this question? So do we need to use a mass deficit method, or I told already it's not a principle mass deficit, but we can start with that if you want. So is it it's better to use with the mass deficit method, or just can we write total energy conservation, total mass energy conservation? So yeah, I think it's better to start with total mass energy conservation. So if you use that, you can include the kinetic energy of the alpha particle also in your total mass energy equation. Okay, so I'm going to erase this and I'm going to work it out now. Okay, so if I use the total mass energy relationship, so you know we can't add mass with energy, so we need to convert the mass to its equivalent energy. So alpha particles, anyway it's at rest, nothing is mentioned about alpha particles, so I don't need to write the kinetic energy of the sorry, not alpha, the aluminium nucleus. Alpha particle has kinetic energy, aluminium nucleus nothing mentioned about it, so we can assume the aluminium nucleus is at rest. Okay, so the energy equation I can write like this. Mass of aluminium C squared, so that's the equivalent energy of mass of the aluminium nucleus, plus kinetic energy of aluminium, but anyway I'm just showing it, but anyway it's 0, nothing is mentioned about it, plus mass of alpha C squared plus kinetic energy of alpha must be equal to initial total mass energy must be equal to kinetic mass of phosphorus, P stands for phosphorus, C squared, that is the equal energy of the phosphorus nucleus, plus kinetic energy of phosphorus, mass of neutron C squared plus kinetic energy of neutron. The question is, find the total kinetic energy of the product. So I can write this kinetic energy of phosphorus plus kinetic energy of neutron together as capital E, because I need to find together. So I don't want to write separately now. So I can just rearrange it like this way: mass of neutron C squared, mass of phosphorus C squared plus mass of neutron C squared plus capital E. These two together I can write as capital E. So I'll change it now, that one. So it could be written as mass of alpha C squared plus capital E. So that includes both kinetic energy of the mass of not alpha, the phosphorus, this neutron, sorry, that E includes the total kinetic energy of the phosphorus nucleus and the total kinetic energy of the neutron. Together I wrote it as E. Okay, now we'll rearrange it. We need to find this one, and also I know the aluminium was at rest, so this kinetic energy equal to 0. But kinetic energy of alpha is given 5.3 mega electron volt. It's given in mega electron volt. Okay, we'll rearrange it now. So if I rearrange it now, it will become like this. Mass of aluminium minus plus mass of alpha minus mass of phosphorus plus mass of neutron C squared plus kinetic energy of alpha is equal to E. I rearrange it, that's all. Mass of aluminium plus mass of alpha minus mass of phosphorus, mass of neutron, altogether C squared. I took the C squared commonly, plus kinetic energy of alpha. Okay, so this one we call mass deficit. Total mass of the initial nuclei, initial elements, that is mass of the aluminium plus mass of the alpha particle minus mass of the product, mass of the phosphorus plus mass of the neutron. So we are subtracting total mass of the products from the total mass of the elements involved, aluminium nucleus and alpha. So that means this is the mass deficit. So you can start directly with mass deficit. So in case if you are starting directly with mass deficit, you should put the kinetic energy of alpha with the mass deficit. Say like that. If you are not starting from here, and if you want to start like this, yes, you can write delta M C squared plus kinetic energy of alpha. This is the total kinetic energy of phosphorus nucleus and the neutron. You can start directly like this, no problem. They accept in the marks. Okay, so this is from the basic principle, like a first principle. We don't call it first principle, something like that. From the basic principles, that is total mass energy conservation. From that, when I start, it comes like that. But anyway, finally, it ends up with mass deficit. This whole portion is the mass deficit. This whole thing is the mass deficit. This is mass deficit. Okay, so you can write directly plus kinetic energy of alpha. Okay, so now I need to consider the energy release due to this portion, and with that I need to add the kinetic energy of the alpha. That's all, not a big issue. Right, so only thing I need to convert the total energy belongs to this portion into mega electron volt. Okay, so mass of the aluminium nucleus, mass of the alpha particle, all are given in terms of unified atomic mass units. So we'll find it. Mass of the mass of the aluminium, that is 1.007276. I wrote it and erase it on the board. Sorry, mass of aluminium is 26.98154 plus mass of the alpha particle, that is 4.001506 minus mass of the phosphorus 29.97831, mass of the neutron 1.008665. So this all mass had to be converted to kilogram multiplied by 1.66 10 to the power minus 27. Is it? So now we converted into kilogram. So solve this, you will get it in kilogram. So you will get minus. So I can call this whole thing as delta m. So this whole thing, the whole thing without multiplying by c square. So when I find the delta m, that is mass of the aluminium nucleus plus mass of alpha particle minus mass of the phosphorus nucleus plus mass of the neutron, I converted into kilogram directly. So that is the delta m. So this is delta m, because my aim, I want to find the energy related to this portion, mass deficit. Okay, so that mass deficit becomes negative. Doesn't matter. That becomes minus 6.522 into 10 to the power minus 30 kilogram. Okay, we'll find the energy equivalent to this mass deficit, this portion only. With that, I need to finally add the kinetic energy of the alpha particle to find the total energy release in the form of kinetic energy of phosphorus and the kinetic energy of neutron. So I'm doing now this, what I put as circle red color. So that portion only I'm doing it. Okay, so the energy released due to this portion, I call it as E1 is equal to delta M times C squared. So the total energy release, I need to add finally this kinetic energy of alpha with this energy. Okay, so that will be equal to minus 6.522 10 to the power minus 30 into 3 into 10 to the power 8 all things squared. So I need to convert to mega electron volt because this is given in mega electron volt. So divide by mega electron volt 10 to the power 6 into 1.6 10 to the power minus 19. So finally you will get it, this part, that will be equal to minus 3.67. That is E1 equal to minus 3.67 mega electron volt. So that is the energy equivalent to this mass deficit. So actually mass is not deficit, mass is increasing. Mass is increasing. The final total mass is more than the initial total mass. That's the reason we are getting negative answer. Okay, so I need to find capital E, the energy release in the form of kinetic energy of phosphorus and neutron. So that will be equal to, I'll erase it and do it. So remember that E1, that is equivalent to this energy, mass deficit is equal to minus 3.67 10 to the mega electron volt. Okay, so finally energy in the form of kinetic energy, I need to find it. So that is E is equal to, that's energy release. This energy E is equal to delta M C square plus kinetic energy of alpha. Kinetic energy of alpha. This is equivalent to this one. So that is minus 3.67 plus 5.3, you will get final answer 1.63 mega electron volt. So sometimes you might think we know how to include the kinetic energy of the alpha. This is the way we include the kinetic energy of alpha. You can start directly with this one without considering this one, but actually you should know the principle. What we are using is the total mass energy conservation, or conservation of total mass energy is the actual theory related to this nuclear decay. But here we accept, normally Marxian they accept even if you start with this equation, but you need to add the kinetic energy of alpha with the mass deficit into c square plus kinetic energy of alpha is the total energy release. Okay, so here again I want to tell you the in this question, January 2015, WPH05 question 15, the energy equivalent to this mass deficit is negative answer. That means there is no mass deficit, mass increased. The final total mass is more than the initial total mass. That's the reason we are getting mass deficit as a negative value, and the energy related to mass deficit also becoming negative. But anyway, when we add the kinetic energy of the alpha particle, finally we are getting energy released which is positive quantity. Okay, sometimes they can ask a question without giving the kinetic energy of the alpha. Then what to do? Don't consider the kinetic energy of alpha. Add the value of kinetic energy of alpha 0. Okay, so then you might think if I put kinetic energy of alpha 0, I will get a negative answer. But anyway, the same type of question appeared again during October 2022. Exactly the same question. October 2022. Same question, exactly the same question. October 2022, question 18. Which is WPH15 paper, but there we are not getting negative answer. So in that question, in this paper, exactly the same interaction, the same question they asked, find the energy released in the form of kinetic energy of phosphorus and neutron. But in this question, the kinetic energy of the alpha is not given. So I need to ignore this kinetic energy. I can't add any value for that. So there the energy release is equal to exactly mass deficit to c square, but we are not getting mass deficit negative answer, because in that question the mass is given in terms of mega electron volt over c square. You know, mass has equal energy, unit 4 you learned. Mass of a particle can have a unit mega electron volt over c square in that form. So they gave the mass in giga electron volt over c square. So only a slight difference. Maybe approximation would have given positive answer. So in that question, the kinetic energy of alpha is not given. The mass of aluminium, alpha, phosphorus, neutron, all are given in this format, giga electron volt over c square. And when we calculate the mass deficit, which becomes positive quantity, not a negative quantity. Anyway, according to the given data, we should accept and do it. So it becomes positive quantity, and the kinetic energy of alpha is not given, so we should assume 0. So there the energy release will be equal to exactly only due to this part. That means there the energy release is only due to mass deficit. Okay, I'll give that question now. So this is the question, this is the data given. So their kinetic energy of alpha particle is not given. Sorry, I didn't visit. The kinetic energy of alpha is not given. So I need to find the energy released in this reaction. Okay, so I can use either total mass energy conservation approach or mass deficit. You will end up with the same answer. So if I use the total mass energy relationship, mass of aluminium c square plus kinetic energy of aluminium, I don't need to write because nothing mentioned about the kinetic energy of aluminium. Anyway, I'll write it. Kinetic energy of aluminium plus mass of alpha c square, kinetic energy of alpha plus mass of equal to mass of phosphorus c square plus kinetic energy of phosphorus. I'm going to put it separately. Mass of X, because X is neutron, they put it as X there. So mass of X C squared plus kinetic energy of phosphorus plus kinetic energy of X is the total energy they asked to find it. So that I put it E. So E includes both kinetic energy of phosphorus plus kinetic energy of X. We know X is neutron. Okay, so here we know aluminium is at rest, nothing mentioned about it. Alpha particle is at rest. So these two quantities will have zero value. This is equal to 0. Aluminium is equal to 0. Kinetic energy of alpha also nothing mentioned. The previous question kinetic energy of alpha was given, but here it's not given. So you may rearrange this equation. It will become mass of aluminium plus mass of alpha minus mass of phosphorus plus mass of X, that's a neutron, into C squared is the energy release. We know this is mass deficit. You can start, again I'm telling you, can start directly with that. But why am I showing this equation means, actually what we are using is total mass energy conservation. There's nothing called mass deficit principle or law of mass deficit. There's nothing called like that in physics, but we accept even if you start with this equation directly. Normally they accept in all exam boards. Okay, right, so now you know that mass of aluminium plus mass of alpha minus mass of phosphorus plus mass of SL, this is the mass deficit. This is the mass deficit. Anyway, we'll find it. Substitute the mass of aluminium is given 25.133. It's in giga electron volt over C squared. So 25.1333. Mass of alpha 3.7274 minus mass of phosphorus 27.9206 plus mass of X is 0.9396. This all in giga electron volt over C squared into C squared equal to E. When I solve it, try it, when you solve it, you won't get negative answer. The same question January 2015 paper, you got negative answer because in this one you are not getting negative answer due to the given numerical values. Maybe a slight different, maybe approximations are giving a positive answer. Whatever it is, when you solve it, you will get this one. 5 into 10 to the power minus 4, 5 into 10 to the power minus 4 mega electron volt over C squared into C squared is the E. So that's going to be 5 into 10 to the power minus 4 mega electron volt is the energy release. If you want, you can convert it into joule. I think the question paper they asked to find the energy release in joules. Anyway, you know how to convert it. 5 into 10 to the power minus 4 into mega 10 to the power 6 into 1.6 10 to the power minus 19 is the energy release. So here you are getting energy release positive quantity, not a negative quantity. So that means both phosphorus and X, the neutron, has total kinetic energy. When you solve it, you will get the answer. But remember that we are using total mass energy conservation. That is the only law we can use in nuclear physics to find the energy release. But we accept even if you start with this format, mass deficit. Okay, so next is about special type of well-known artificial transmutations of fission and fusion. In first lesson, I told that one of the factors that decides the stability of the nucleus is binding energy per nucleon, not binding energy. It should be the binding energy per nucleon. That means if a nucleus, when you compare two nuclei or when you compare two different type of nuclei, one of it has higher binding energy per nucleon means it's more stable compared to the other one. So in my first lesson, I gave the graph binding energy per nucleon against mass number graph. You can find it everywhere in all books. This is mass number or nucleon number. This is binding energy per nucleon. So the shape of the graph approximately something like this. There are could be small fluctuations, then increases and decreases. So this is the iron. Iron has the highest binding energy per nucleon, means iron is the most stable nucleus in terms of binding energy. Okay, so what is nuclear fission means? During any nuclear interactions, if the product has higher binding energy per neutron, means the product is becoming more stable. That means that interaction is possible. Easily it could be done. That will happen mostly with release of energy, but release of energy not completely depends on the binding energy per nucleon. It depends on the, I said in my first lesson, that depends on the total mass energy flow. But anyway, generally if the product has higher binding energy per nucleon, that interaction, nuclear reaction will happen with release of energy. For example, what is fission reaction means? If we break a massive nucleus, something like uranium isotope, uranium-235, it could become it could break up into barium, krypton, or there are many different possibilities are there. It could break up into barium and krypton with release of three neutrons, or rubidium and cesium, or zirconium and tellurium. Like that, many different possibilities are there depending on the kinetic energy of the neutron, which collide with the uranium nucleus. Whatever, I will discuss it later today. But anyway, the products will have smaller mass number, means the products could be somewhere here and here. That means the binding energy per nucleon of the products will become larger than binding energy per nucleon of the uranium nucleus. That means products are more stable than the uranium nucleus. So that reaction is possible with release of energy. We need to give small amount of energy to start the reaction in the form of kinetic energy of neutron. But anyway, there the energy released, the net energy will be released. So the stability of the products will be more than the stability of the initial nucleus, which is uranium. The reason binding energy per nucleon is higher than the binding energy per nucleon of the initial nucleus, which is uranium. Same way, what is fusion means? Joining unstable lighter nuclei. For example, when two hydrogen nuclei join together, or isotopes of hydrogen, something like deuterium and tritium, when they are joined together, they form a helium nucleus. The helium nucleus binding energy per nucleon is higher than the binding energy per nucleon of hydrogen nucleus. So there also stability is increasing compared to hydrogen. Helium has more binding energy per nucleon, stability is more. So there also energy could be released, and that interaction is valid. Okay, so that reaction is called nuclear fusion reaction. So we are going to go in detail about nuclear fission and fusion separately now. Okay, so this is nuclear fission reaction. Normally, most of the textbooks and the past paper, it gives this interaction only, that is uranium-235 absorbs a thermal neutron. I'll come to the point, thermal neutron. So when a uranium-235 isotope absorbs thermal neutron, it becomes barium, krypton and 3 neutrons. But these interactions also possible. The same, the left side you can see exactly the same, all three interactions the same. Uranium-235 absorbs neutron, uranium-235 absorbs neutron, but here barium, krypton 3 neutron, here rubidium, cesium and 2 neutrons, here zirconium, tellurium and 3 neutrons. Why? What's the reason for different types of daughter nuclei? These are called daughter nuclei. Here also we can use the word daughter nuclei. So all products, here the products are different. Here combination of product barium krypton, here rubidium cesium, zirconium tellurium. What's the reason? Which factor decides this different combination of daughter nuclei or products? The reason is, first we can say the kinetic energy of the neutron. So always the kinetic energy of the neutron in the nuclear reactors won't be exactly the same. 100% it won't be same always. So when the kinetic energy of the neutron differs, that also can cause different type of products, first reason. Second reason, closure structure. Nuclear closure structure means, normally when the daughter is produced, it tried to get the proper stable configuration in terms of neutron to proton ratio. So sometimes to get more stable configuration, neutron to proton configuration, the daughter nucleus might emit another neutron. That also can happen. That also can vary the outcome or the products. Third one, we can say sometimes the daughter nucleus, after the first reaction, when the uranium breaks up, so the product could be in the excited state. In my first lesson I told that the energy release could be due to mass deficit, but we learned, or total mass energy conservation. Additionally, there could be energy release due to rearrangement of the nucleons in the nuclear energy level. So here the daughter nucleus, if it is in the excited state, there are also the excited nucleus, when it returns to ground state, it might undergo secondary fission reaction. One more factor, that very less chance, the angle of the neutron, the velocity of the direction of the neutron, because in these all interactions momentum is conserved. It also has a slight effect. The direction of motion of the neutron also can decides the product or outcome of the fission reaction. Okay, so but anyway, but mostly the textbooks and exam papers, they give the first interaction, second and third, but it's given in your Pearson textbook, in the student book 2. It's given as a question on page number 145, student book 2, second A2 book, page number 145. Question number 4 and question number 6 consists of these interactions. So these are, that means you also better know there are different possible outcomes during nuclear fission reaction. Okay, so the neutron is called thermal neutron. What do you mean by thermal neutron? Means, it's in equilibrium with the environment, in terms of thermal equilibrium with the environment. Normally, what could be the kinetic energy of thermal neutron is very low. Actually, the kinetic energy of the thermal neutron is almost in the form of 0.038 or 0.04 electron volt. The kinetic energy of the neutron, thermal neutron, we can calculate. So we can think about the kinetic energy of the neutron, something like it's at a temperature of 20 degrees Celsius or 18 degrees Celsius normally in the normal room temperature. So if you try to calculate the kinetic energy of the thermal neutron, because the kinetic energy of thermal neutron should be lower, otherwise the neutron will not be captured by the uranium nucleus. It will escape without being captured by the uranium nucleus. So it should have a lower kinetic energy, which is we call thermal neutron, which is in equilibrium with the environment. What could be the kinetic energy? We can use the kinetic energy of the neutron by using 3/2 kT. What we use in thermal physics, mean kinetic energy of ideal gas. Here the neutron is actually, we can imagine it's like a neutral like ideal gas particle, because its charge is 0. We can approximately use this. If we use 3/2, the Boltzmann constant 1.38, 10 to the power minus 23, into the temperature almost like 18 degrees Celsius plus 273. So if you find its energy, that will be equal to 6.02 10 to the power minus 21 joule. Convert to electron volt, divide by 1.6, 10 to the power minus 19. Electron volt. So that will be 0.038 electron volt approximately. we can say 0.04 electron volt. So that's the kinetic energy of the thermal neutron. Not much, very low. Okay, so how to calculate the energy released during fission reaction? Okay, so there are two methods. First method, by using total mass energy conservation, that ends up with uh, mass deficit method. Already we discussed in this lesson several times earlier. That is one method. Total mass energy relationship we use. When we rearrange, it becomes mass deficit into c squared. Yeah, so actually the origin of that mass deficit into c squared is the total mass energy conservation. That is one method. The second method, by using binding energy of the uranium, binding energy of the barium, binding energy of the krypton, we can find the energy release if we know the binding energy of each of these nuclei. Neutron has no binding energy because neutron is a free particle. So individual free particle, it has no binding energy. So second method we can find by using binding energy. If we know the binding energy, sometimes questions could be based on binding energy also. Okay, we'll do the first method where we use the total mass energy relationship, or simply I can say that is mass deficit. When we rearrange, it becomes mass deficit. Already I did that. Okay, so the uranium is at rest. Okay, the second question, second and the problem students they normally ask, when we are using this total mass energy relationship, okay, generally it won't be a problem. Normally students they find the mass deficit by mass of the uranium nucleus. From that they subtract mass of the uranium nucleus plus mass of the neutron, that's the total mass. From that they subtract the total mass of barium, krypton and 3 neutron. They find the mass deficit into c squared. Yeah, that's okay. But students normally they ask, do we need to consider the kinetic energy of the neutron when we consider the total mass energy relationship? We'll see whether do we need to consider that. Okay, so here when we consider total mass energy relationship, uranium is at rest, so it has no kinetic energy. So that will become mass of uranium c squared plus mass of neutron c squared plus kinetic energy of neutron equal to mass of barium c squared plus it could have kinetic energy. I'll put all the kinetic energy as the energy release finally. Mass of barium c squared, mass of krypton c squared plus 3 times mass of neutron c squared. Okay. Now this can have kinetic energy, this also can have kinetic energy, this also have kinetic energy. Additionally, there should be energy release in the form of thermal radiation or electromagnetic radiation, everything together, all the energy release. So here I put only the equivalent energy of the masses plus all the energy together, kinetic energy of barium, kinetic energy of krypton, kinetic energy of the 3 neutrons, additionally thermal energy radiated plus any other electromagnetic radiation release, everything together we put E. So that's the normal question they ask, total energy release. Total energy release, they never ask what type of energy, or they don't ask individually how much kinetic energy of this one, how much is the thermal radiation, they don't ask. Total energy release they ask. So that total energy I put it as A. So again, when you rearrange this, mass of uranium plus mass of neutron, you don't need to start like this. You can directly start from the following step. Mass of uranium plus mass of neutron minus mass of barium plus mass of krypton plus 3 times mass of neutron into c squared plus kinetic energy of neutron is the total energy release. So normally exam papers, the mark schemes, they give this as the mass deficit. So the whole thing is given as mass deficit. Total mass of the uranium, mass of the neutron minus total mass of the product. That's the mass deficit into c squared plus, they don't consider this one, kinetic energy of the neutron. Normally we don't consider this factor. Normally in the past papers or in the textbooks, they don't consider this one. We'll see why don't we consider that one. So to give that, so after this you can ignore it, but first I'll work it out and show why do we normally ignore that. Okay, we'll try to find this quantity first. Then with that we need to add the kinetic energy of the neutron to get the total energy release. So we'll solve step by step. First we'll find this part. This portion we'll find it first. Delta M C squared, I'm going to find it, this part. With that, if I add the kinetic energy of the neutron, that will be the total energy release. Also, I told you can start with this one in the exam. It's not necessary to start from this one. Okay, we'll find this one first. Delta M C squared. So, mass of uranium 235.0439 plus mass of neutron. I can say mass of neutron minus mass of 2 neutron. You are right, no problem. So again I have to subtract 3 neutrons. 1.008665 minus mass of barium 140.9144 plus mass of krypton 91.9262 plus 3 times mass of neutron 1.008665. Okay, so find the into C squared. Okay, so I'll find the mass deficit first, easy. So find the mass deficit first, then I'll multiply by C squared. So find the mass deficit, you'll get 0.1806, 0.1860 U in unified atomic mass. Unit convert to kilogram, 0.1860 into 1.66, 10 to the power minus 27 kilogram. Right, now find the equivalent energy, that is delta M times C squared. We will find it now. Okay, so that will be equal to 3.0876, 10 to the power minus 28 kilogram. Anyway, we find the energy release in terms of mega electron volt. So you know the mass deficit 3.0876 10 minus 28. I'll trace it because I need the space. So I'm going to find the delta MC squared in mega electron volt. So that is delta MC squared. That is this portion I'm finding. So I found it delta M 3.0876 10 to the power minus 28, 3 into 10 to the power 8 all things squared. So I'll get it in joules. I will convert to mega electron volt. Normally we give it in electron volt or mega electron volt. That's a general format we give. So to convert mega electron volt, divide by 1.6 10 to the power minus 19 to convert electron volt, 10 to the power 6 mega electron volt. So there you will get the final answer 173.7 mega electron volt. So total energy releases, I did this portion now. This is the part, this part, delta M C squared, 173.7 mega electron volt. Kinetic energy of neutron, I gave it 0.04 electron volt. Okay, 0.04 electron volt. So the total energy released is equal to delta MC squared, that is mass deficit into C squared, which I got from the conservation of total mass energy, plus kinetic energy of neutron. Kinetic energy of neutron is 0.04 electron volt compared to this negligible. So 173.7 mega electron volt plus 0.04 electron volt. I worked it and show it half. That is, I told that the 3 by 2 kT, that format I did it. So when you solve it, you'll get the final answer. Normally we don't consider this amount. So 173.7 mega electron volt. So during calculation related to energy released during fission reaction, we don't need to consider the kinetic energy of the neutron. We can ignore, we don't need to consider, because the energy released due to mass deficit is much higher than kinetic energy of the thermal neutron. So that's the reason we don't consider normally. So here also again I am telling it, it's not necessary to write the actual mass energy relationship. You can start directly from the mass deficit method, but in case if they give the kinetic energy of neutron, but normally they don't give because it's very small, you have to add the kinetic energy of the neutron with the energy equivalent to mass deficit. This is the energy equivalent to mass deficit. With that, the kinetic energy of the neutron should be added. Then only we'll get the total energy released during fission reaction. So to show that only, I wrote this format. But exam wise, you can start directly from mass deficit and you don't need to consider this one now. I already showed it. So the energy release is equal to mass deficit into C squared. Okay, so second method, how to calculate the energy release during fission reaction. So we know that we don't need to consider the kinetic energy of the neutron, thermal neutron, we don't consider, right? Okay, the first method I showed it, mass deficit approach we can do. Second method, binding energy. So sometimes the question paper might give the binding energy of uranium-235, barium-141 and krypton-92. They might give, or if they want to extend the question, they might ask you to calculate. You know how to calculate the binding energy. I already discussed it in my first lesson of this nuclear decay. Go through it. The link is given in the description of this video. Okay, so you can calculate the binding energy if you want, or you might use the already given binding energy. It might slightly differ when you check it with the internet. It's okay because the mass of the proton, they sometimes use slightly different decimal points, so that can cause slightly different values in binding energies. Anyway, so the energy release, how to calculate, that's simple. Binding energy, less work. So energy release in the form of together kinetic energy of barium, krypton, neutron and thermal radiation, everything together. So the total energy release is equal to binding energy, I put B dot E dot, binding energy of barium plus binding energy of krypton minus binding energy of uranium. Neutrons have no binding energy. Substitute here. Binding energy of barium given 1148.12 plus binding energy of krypton that is 766.59 minus binding energy of uranium 1741.06. Solve it. You will get 173.7 mega electron volt. Exactly the same answer what we got when we use the total mass energy approach or mass deficit method, whatever, both same. So there we are getting the same answer as what we are getting now. U stands for uranium, Kr krypton, barium, Ba. Okay, so next thing is about energy released during nuclear fusion reaction. Normally we learned that when two hydrogen nuclei get closer to each other to get fused, there will be much large electrostatic repulsive force. To overcome it, they should have higher kinetic energy. That higher kinetic energy is achieved by using higher temperature. Now when you think about higher temperature, how much is the possible maximum temperature? When you think about core of the sun is almost 15 million Kelvin. 15 million Kelvin. Even 10 million Kelvin is okay for fusion to overcome the electrostatic repulsive force, but sun has 15 million Kelvin. Okay, how much will be the kinetic energy of deuterium and tritium at the temperature of 15 million Kelvin? We can calculate that first by using the same equation what we use in thermal physics. Kinetic energy equal to 3 by 2 kT, approximate way we can calculate it. So there are 3 by 2 kT means K is the Boltzmann constant, So 3 by 2, 1.38, 10 to the power minus 23. That's a Boltzmann constant. Temperature, if I say 15 million Kelvin, so 15 into 10 to the power 6. To solve it, you will get it in joules. That will be equal to, converted directly, mega electron volt 10 to the power 6 into 1.6, 10 to the power minus 19 mega electron volt. So that will be equal to 0.00194 mega electron volt. So normally at a very high temperature of 15 million Kelvin, these particles, deuterium and tritium, we can write the deuterium by D21 and tritium by 3T1. Those are the normal standard notations for isotopes of hydrogen. Anyway, you know that. So the kinetic energy of them will be 0.00194 mega electron volt. But if we think about this, the extreme situation, something like really we get, but if this has something like rather than 15 million Kelvin, 1 billion Kelvin, that's the worst, much higher temperature. In that situation also, it will be 0.13 mega electron volt. Still the kinetic energy is lower. We'll see how much do we need to consider, normal students they ask, when we calculate the energy release during fusion reaction, here also students they ask as what they ask in normally fission reaction, do we need to consider the kinetic energy of the neutron? Here also normally you would have done it at school. When we find the energy release during fusion, we consider mass deficit. We don't consider the kinetic energy of deuterium and tritium, but we say they should have higher kinetic energy to overcome the electrostatic repulsive force. We say so many things, but we don't consider their kinetic energy when we calculate the energy release. We'll see why. Remember the value. If it is a very high extreme temperature, 0.13 mega electron volt, but normally in the sun, the core of the sun, that is 0.00194 mega electron volt. Okay, now we'll calculate the energy release during nuclear fusion reaction. Okay, so deuterium, tritium fusion reaction. Here also we can find the energy release in two different ways as we did in nuclear fission reaction. First, we can find the energy release by using total mass energy conservation, total mass energy conservation that extends to mass deficit into C squared. Yeah, both I already several times I showed it. When we start with total mass energy conservation, it ends up with mass deficit into C squared. But the problem here, we need to check whether do we need to consider the kinetic energy of tritium and deuterium due to the higher temperature. They should have kinetic energy, but do we need to consider when we calculate the mass deficit? When we calculate the energy release during fusion reaction. So the first method by using that way, total mass energy conservation or the binding energy approach, mass deficit approach. The second method, binding energy. By using binding energy also we can calculate the energy release. Okay, first method. So here we'll find the mass of the 3H1 means that is the that's tritium, deuterium, helium, right? Neutron masses are given in terms of unified atomic mass unit. Okay, we'll start with the approach of total mass energy conservation. So mass of T C squared, T stands for tritium, kinetic energy of tritium plus mass of deuterium C squared, kinetic energy of deuterium, okay, equal to mass of helium C squared plus mass of neutron C squared. Then kinetic energy of helium plus kinetic energy of neutron plus thermal radiation, all type of energy released together, I put it as E. We need to find this E. Rearrange it. So when you rearrange, it will become mass of T, tritium, plus mass of deuterium minus mass of helium plus mass of neutron into C squared plus kinetic energy of deuterium plus kinetic energy of tritium is the total energy release. So this is the mass deficit. See, we ended up with mass deficit, but there's no principle or law called mass deficit. But anyway, we end up with this one. Okay, we'll substitute and we'll first find this one. So this I can call delta M. So this whole thing I'll call delta M C squared plus kinetic energy of deuterium plus kinetic energy of tritium equal to E. That's a total energy release. Do we need to consider this one? Do we need to include this one with this one to find the total energy release? We'll see. After that, I can give the conclusion whether we need to include or not. Okay, we'll find this one, delta M. We'll find the delta M. Substitute. So delta mass of tritium, tritium 3.0155. Then that is mass of tritium, mass of deuterium 2.0136 minus mass of helium 4.0015 plus mass of neutron 1.008665. This is in unified atomic mass unit. So you will get delta M 0.018935. Convert to kilogram, 0.018935 into 1.66, 10 to the power minus 27 kilogram. So you will get that will be equal to 3.143, 10 to the power minus 29 kilogram. Okay, so find the energy release delta MC square. We'll find delta MC square 3.143 into 10 to the power minus 29 into 3 into 10 to the power 8 all things squared in joules. Find it in mega electron volt. So that is, we'll write it here. So convert this to mega electron volt. Whatever the answer you get, that will be 2.829, 2.829 10 to the power minus 29 joules divided by 10 to the power 6 into 1.6, 10 to the power minus 19 mega electron volt. You will end up with 17.7 mega electron volt. Okay, now think about the total energy release E is equal to this value. Is it total energy release E? That total energy release E is equal to energy release due to mass deficit, which comes in this bracket, that is 17.7 mega electron volt, plus the total kinetic energy of deuterium and tritium. So we found the total kinetic energy, individually we found it. Say if it is in the sun, which is 0.009194, so plus 0.00194, just for one particle. There are two particles, deuterium and tritium, into 2. Even if you multiply by 2, compared to this, this is much smaller. 0.00194 into 2, because I multiply by 2, this is for one particle at 15 million Kelvin. I calculated just now earlier when I start this fusion. So this one I did it already, I raised it. So 0.00194 into 2. Even if you consider the extreme condition, which is 1 billion Kelvin, there the energy will be 0.13 mega electron volt, 0.13 into 2, that is 0.26, both together 0.26 mega electron volt. Compared to this, this is much smaller, even for the extreme temperature, something like 1 billion Kelvin. Is it? So that's the reason. Remember that when we calculate the energy release, the very common question students they ask, do we need to include the kinetic energy of deuterium and tritium. No, you don't need to consider, because the energy released due to the mass deficit is much larger compared to the kinetic energy of both deuterium and tritium, even at that much higher temperature. So we don't consider that. So we can say the energy release is almost 17.7 mega electron volt. That's the energy release. We don't need to consider this part, the kinetic energy of deuterium and tritium. We don't need to consider. Exam view, you can directly write this one. So we don't need this part, kinetic energy of deuterium, tritium, we don't need. So the energy release, that is equal to E, I'll put it in greening. The energy release is equal to mass deficit into C squared. That's all, simple way you can write the energy release during fusion reaction. We don't need to consider the kinetic energy of deuterium and tritium. Okay, second method, I told we can find the energy release during fusion by using binding energies. So here we can write the energy released is equal to binding energy of helium. Neutron has no binding energy, minus, because it's an individual particle, free particle, minus binding energy of tritium plus binding energy of deuterium. Or I can say, if it is confusing, I can say 3T1 plus binding energy of 2D1 deuterium, tritium. Okay, substitute that He42. Right, binding energy of helium is 28.369. Or you can calculate, if you know the mass, you can calculate the binding energy. As I explained in my first lesson, minus binding energy of tritium is 8.503 plus 2.186. Solve it. You'll get exactly 17.7 mega electron volt. Same thing what we got in the first method, where we use mass deficit approach or mass energy equivalence. We don't need to consider the kinetic energy of deuterium and tritium due to the kinetic energy, due to the temperature. We don't need to consider, it's much smaller. Okay, this is the second method. B dot E stands for binding energy. Okay, so when we consider fission and fusion reactions, which one is more efficient in terms of energy release? Okay, so we'll calculate which one is more efficient means we can calculate by considering the same amount of fuel, nuclear fuel. So whether 1 gram of uranium when we use, or 1 gram of total deuterium and tritium, 1 gram. Okay, we'll try to find out which one is more efficient. So when we consider uranium, so mass of uranium compared to mass of uranium, mass of the neutron is negligible. So we already calculated the energy release. So we know the mass of uranium U-235, that is 235.0439 unified atomic mass unit. So when one uranium undergoes fission reaction, the energy release is 173.7 mega electron volt. That means this we convert to kilogram, that is 235.0439 into 1.66 10 to the power minus 27 kilogram. When it undergoes fission reaction, the amount of energy release is 173.7 mega electron volt. So we'll see how much of energy will be released when 1 gram of uranium is used. When 1 gram of uranium used, how much of energy release, divide this by this amount and again divide by 1000 to convert. If I divide this by this, I'll get the energy release by 1 kilogram, but I want to find by 1 gram. So again divide by 1000, you will get, that will be 339, sorry, that will be 71.22 kilojoules. Okay, I'm comparing it in joules, so you have to convert this to joules by multiply by 1.6 10 to the power minus 19, and it's not an issue. So anyway, I'm giving it in joules, so that it becomes 71.22 kilojoules. This is for fission reaction. Okay, when we consider fusion reaction, how much of mass involved? When we consider total mass of deuterium and tritium. So mass of deuterium, we know that mass of deuterium 2.0136 U, mass of tritium, that is 3.0155 unified atomic. So totally when we consider, that is 5.029 U unified atomic mass. That's a total mass of a deuterium and a tritium. When it involves, the energy release is 17.7 mega electron volt. We know how to convert to joule, 10 to the power 6 into 1.6 10 to the minus 19. Anyway, I'm keeping it in kilojoule, easy to compare, right? That's nothing. Okay, so when 1 gram means you have to convert this to 5.0291 into 1.66 10 to the power minus 27 kilogram into gram means 1000 grams. When 1 gram involves, how much of energy will be released? When 1 gram involves, that means you have to divide this by this amount. So that means this gives 17.7 mega electron volt. So 1 gram, how much? Divide this by this, convert to joule, multiply by 1.6 10 to the minus 19, you 10 to the power 6. You will get 10 to the power 19. So convert to joule, this is into 1.6 10 to the power minus 19 into mega 10 to the power 6 joules. Anyway, you know how to convert it. Right, when you convert that, 1 gram will give 339 kilojoules. Check it, 339 kilojoules. This is gigajoule, not megajoule, gigajoule. This also gigajoule, that's a mistake. Okay, so giga, that is 10 to the power 9 joules, 71.22 gigajoule. This will be 339 gigajoule, 10 to the power 9 giga. Okay, so you can see energy released during fusion. When we consider one total mass of 1 gram of fuel, here 1 gram of uranium, here 1 gram of both together, deuterium and tritium together, 1 gram when we use, the energy released during fusion is 339 gigajoule. Yes, that's right, 339 gigajoules. And this is 71.22 gigajoules. So you can see how much it's much higher than this one. Okay, so fusion is more efficient in terms of energy release, but there are other advantages of fusion. You know that during fission reaction, the products are highly radioactive, like barium, krypton are highly radioactive, but here only the product will be helium, so more clean. Actually, fusion is clean, energy release is more and cheaper actually compared to uranium. Hydrogen is much cheaper. Not only deuterium, tritium, even just we can have fusion with hydrogen isotopes, but they are naturally exist and much cheaper. So those are the advantages of fusion compared to fission. But there are a lot of difficulties having controlled fusion reaction. The difficulty is achieving such high temperature in a controlled fusion reactor is not possible, because to get such high temperature we need much higher thermal insulation, much stronger thermal insulation, but there will be large amount of heat loss to surrounding, so difficult to maintain such high temperature. with less amount of heat loss. So if there's heat loss to surrounding, then the problem is heat should be supplied, so there won't be any net energy output. The second problem is to continue the fusion reaction, to sustain the fusion reaction, the rate of collision should be much higher. To have such higher rate of collision, the density should be much higher. So very strong magnetic field is required to keep such higher density. But in stars, naturally they have inward gravitational pressure. So due to the inward gravitational pressure, they are able to continue the fusion reaction inside the core. I already discussed my astrophysics cosmology. The link you can get it from the if you go to playlist, there you can go to lessons in unit 5. There you can see the cosmology lesson. Yeah, so the stars have large inward gravitational pressure that keeps the density much higher. So these are the difficulties in terms of fusion reaction compared to fission reaction. Okay, so that's all related to your nuclear decay in unit 5. There are 3 lessons. I already discussed all 3. So completely I finished the nuclear decay. First lesson, binding energy and the stability. Second lesson, radioactive decay. Third lesson, artificial transmutation, including fission and fusion. So that's all the topic related to nuclear decay. I might discuss more questions separately later as separate videos. If you subscribe this channel, you will get notifications. Also, see the playlist. There all my 100 videos are classified into different units, so you can navigate to the required lessons related to the required unit. Okay, so I hope you understood. Bye.